So good afternoon, everyone. Good afternoon, everyone. We are the Group 3 and we will discuss the beam-based effect localization techniques. We are Ricia DELATORE, yours truly, Austin IKAN, and Franco VILLAREAL. So at the end of the presentation, these are the following points that students should know. So we will proceed to the presentation itself. So introduction, SEM and SOM techniques take advantage of the active injection. So active injection refers to the techniques that alter the electrical characteristics of the device analyzed. These techniques can also be performed using the proper laser wavelengths. So why should we use SEM? So SEM is the scanning electron microscopy. This is preferred over optical microscope since it can greatly increase the depth of the field, much higher magnification, increased working distance, and improved imaging of surface topography as can be seen in the image beside. So the specimen is really magnified several times. Another one is the SOM or the scanning optical microscope. So it is a valuable tool for photo beam-based analysis of ICs. It can produce the reflected light images of improved spatial resolution and depth of field compared to conventional optical microscopy. So SOM is one of the main vehicles for backside failure analysis tool development. So we'll now proceed to discuss some of the electron beam techniques used in the IC failure analysis. So one is the electron beam induced current or EBIC. It is primarily used to identify the buried diffusion and silicon defects and also imaging localized regions of Fermi level transition. So the physics behind its technical use is that when the primary electron beam is scanned across a sample, many interaction products are generated as can be seen in the photo beside. So primary beam is dropped onto the device surface. It then creates a secondary electrons and backscattered electrons. Also, collisions between primary electrons and target material form electron-hole pairs wherein a single 10 kilo electron volt primary electron can produce as many as 500 to 1,000 electron-hole pairs. Another is that a large number of pairs per electron generates an EBIC signal in which its magnitude and direction of the induced current is used to generate an image localizing where junction potential occurs. This is primarily the purpose of the EBIC technique, to locate where the junction potential occurs. So EBIC imaging requires an SEM, a current to voltage amplifier, and an electron vacuum feed through. So possible damage that can occur using this technique is that physically there is none, but irradiation damage occur to gate oxide of MOS transistors when alteration of threshold voltage is done. The figure beside is an example of the EBIC imaging of an entire die. So next technique is called resistive contrast imaging or RCI. It generates a relative map between two nodes of passivated integrated circuit. So the physics behind RCI is that it uses an integrated circuit as a complex current divider to obtain the resistance information. Also, to obtain the RCI info, the primary electron beam energy is increased until the tip of the interaction volume intersects the buried conductor of interest. As can be seen in these three figures, first figure is that we can see that the current amplifier or an amplification is required for RCI, and then the current induced by the electron beam exposure will have a path out of the IC. On the A and B figures, we can see that these are the example of RCI imaging locating an open conductor. So it localizes an electromigration open along a clock line. And for this B figure, BSE or the backscattered electron image of a similar view at 30 kilo electron volts. So RSI is the same with EBIC, requires SEM, current to voltage amplifier, and electron vacuum field through. Also, the sample preparation needed is a lead or plastic of package removal. For this one, no electrical driving equipment needed since the IC is driven only by the electron beam. And unfortunately, not all internal conductors with defects will be identified using the RCI. So for the same with the EBIC, there's no physical primary damage, but there's also no direct primary electron or gate oxide interactions occur. However, some bremsstrahlung X-rays generated by interactions in the passivation layer will deposit energy in the gate oxide. This X-ray dose will alter the interface trap density and occupancy as well as the fixed charge levels in the gate oxide. Next technique is called charge-induced voltage alteration imaging or SIVA. So this technique was developed to localize open conductors on both passivated and depassivated CMOS ICs. Also, SIVA facilitates localization of all open interconnections on an entire IC in a single unprocessed image. SIVA also has been applied to an analog bipolar technology with similar results. So the reason for the functionality of SIVA is that there's a significant quantum mechanical electron tunneling. So across the open that can transport enough charge at low frequencies to maintain the functionality. So the physics behind its use is that CMOS ICs with open conductor lines may function at low to moderate frequencies, such as those less than 50 kHz. So SIVA takes advantage of this tunneling capacity to create an image of loaded areas. Also, the SIVA image is generated by monitoring the voltage shifts in constant current supply as the electron beam is scanned over a biased integrated circuit. So, transistors with weak drive capacity have also been identified using SIVA. So, these are some of the things that can be analyzed in the failure analysis of an IC using the SIVA. So, the difficulty to implement is that, like RCI, the selection of proper electron beam energy includes using energies that just reach the buried conductors and avoid the EBIC signal generation. Aside from that, it can possibly damage the IC. It also requires the SCM, but it needs a constant current source. And for the possible damage, same with the RCI imaging, no direct primary electron gate oxide interactions occur. So as we can see in this figure, this is the experimental setup used to generate the SIVA or the SIVA images. So SCM is used, and then it is coupled by the amplification, AC coupled amplification, wherein the image is acquired, and then the graphical display or the SIVA image will be obtained. And in here, it shows an example of the SIVA imaging on the passivated IC with an open conductor. So another form or another techniques is the SIVA using low primary beam energies. So this one is that similar with the SIVA previously, but it is operated at low primary beam energies. So it is operated at less than 1 kilo electron volt that localizes open metal conductors beneath the passivation layers with conventional SIVA. So the major difference between the two approaches that low beam energy SIVA, or also called less SIVA, does not introduce any irradiation damage to the IC under test. Since nga, it operates at low beam energies, so it does not introduce any irradiation damage. So the physics behind this is that conventional SIVA localizes open conductors on an IC by powering the IC with a constant current source and monitoring the voltage fluctuations in the power supply with the electron beam position. In addition, most electron beam testers have a fixed primary electron beam energy at around 1 kilo electron volts, and SIVA at low primary beam energies circumvents problems by producing the SIVA image of the buried IC conductors without direct interaction. So as we can see in this figure, the low energy SIVA images of an open conductor, these three, And also, these images required using a 300 electron volt primary electron beam energy.
For the last electron beam techniques, recent low energy, SEM, and solution improvements. So it is not an active SEM technique, but improvements yielding a smaller energy distribution in the selected primary electron beam energy, and biosample approaches have increases the spatial resolution of the SEM for a low voltage application. So these improvements are applicable to enhancing multiple SEM techniques. And monochromators in the upper SEM column yield a smaller energy spread and hence the ability to focus a smaller spot to a low beam energies. So therefore, the samples that were previously too fragile for higher resolution SEM imaging can now be observed at a low energies with a spatial resolution of 1 and nm or a better reported beam with a 500 electrovolts or greater. The next is the recent low energy SEM resolution. As you can see the figure display, it is a uncoated pyrolyzed photoresist with gold particles using a monochromated 500 and 300 electrovolts primary electron beam. So letter A is a 500 electrovolts primary electron beams and the letter B figure is a 300 electrovolts primary electron beams. So if the sample can be biased positively, the interaction or landing energy can be reduced further while still maintain improved spatial resolution. Next is so here are some optical beam based techniques discussed by uh, first is optical beam induced current or OBIC is a scanning optical microscopy SOM imaging mode that localizes regions of Fermi level transition. Um, uh, i- OBIC is primarily used to localize barrier diffusion and semiconductor defects. Minority carrier diffusion lengths and lifetimes have also been measured using OBIC, but these are very rarely applied during failure analysis. So this is a physics behind the tool use. The basic SOM consists of the focused light spot normally from a laser source that is scanned over a sample. Some property of the sample is observed. This property is to produce an image of the sample as the spot is scanned. The scan may achieved by their scanning sample in a light spot. The additional testing information can be useful in selecting optimum condition for performing OBIC. OBIC mode SOM is very similar to EBIC, like what I said earlier, mode scanning electron microscopy. If the photon energy and the incident light is greater than the semiconductor band, gap electron hole pairs are formed as light penetrates the semiconductor. So here are the physics of OBIC signal generation figure. Next one is OBIC image of unbiased CMOS device made by observing current of VDD and VSS. Um, so the possible ice damage, it has no physical damage occur with an SOM examination. But if a bias of VIC is used, it is also possible to initiate a snapback or latch up condition in the bias integrated circuit. And also the damage can be avoided or mitigated by prudent selection of the light source. And the current compliance is biasing power supply. So the next one is um, the light-induced voltage alteration or the LIVA. So the information tool yields is a LIVA is a scanning optical microscopy (SOM) techniques that develops to localize diffusion associated with integrated circuit. So LIVA should not be confused with OBIC or optical beam induced current. The LIVA is signal derived from a voltage fluctuation on a power supply where areas the OBIC signal is generated by a current flow at a specific junction on the IC. And LIBA approaches has also been used to identify the logic states of the transistor with much greater sensitivity than previous optical techniques. So the physics behind tool use is the most widely known SOM technique utilizing electron hole pair generation is optical beam inducing. And also LIBA, like OBIC, techniques advantage a photon-generated electron hole pairs yield to IC function and effect information. So the next is LIVA is an optical beam polarly to the electron, and the difficulty to implement the equipment necessary to perform LIVA imaging are scanning optical microscope, a constant current source voltage amplifier, preferably AC coupled and with electrical connection to the IC examination. So the IC must be biased in a non-contention state, but no complicated vector is required. So possible IC damage, there's no possible IC damage in SOM, but there are two possible damage scenarios for ICs. Number one is erasure for non-volatile memories, which are susceptible to certain light energies, and number two is creating snapback or lash up condition in IC bias in a bias IC like in OBIC.
So thank you for that report. So the next part is fault localization. After knowing that you have a faulty chip, the next is localizing where the faults are. There are the next technique are thermal beam induced techniques, which can be also divided into three parts: the Oberth, TIVA, SEI. Oberth stands for optical beam induced resistance change. TIVA stands for thermally induced voltage alteration, and SEI for Seebeck effect imaging. So for beam induced techniques, this can be grouped into two. Oberth and TIVA are for shorts, while the SEI is for opens or open circuits. In Oberth, it permits examination of entire IC die in a single unprocessed image. It is also the same with TIVA. So what it means here that an IC can be observed from either the front and either the back. So for TIVA, the localized heating changes the resistance of a short site, also with Oberth. Um, and these thermal beam induced techniques uses an infrared laser wavelength longer than 1.1 micrometer. This another this is the length of the indirect band gap in silicon to produce localized heating on an IC without electron hole pair production. So this is important that if the short is a conductor, the resistance will increase with temperature. While if the short site is a semiconductor, the resistance will decrease with increasing temperature. So as I said before, that for short sites, Oberth and TIVA are used, while for opens, SEI is used. So localized heating can also be used to locate open conductor sites from the front and the backside of an IC. So as I said before, if TIVA and Oberth can locate short conductor sites, SEI can also do the same, but for open conductor sites from the front or the back. So open conductor sites are identified through the use of Seebeck effect. So the signals can be small depending on the details of the defect, especially for SEI. Therefore, increased laser power will produce stronger signals for all the techniques. So next slide. So the difficulty to implement these thermal beam induced techniques is that the equipment necessary to perform all the three techniques are scanning optical microscope, so SOM, with the power with the proper wavelength laser, a constant voltage over or current source for TIVA and SEI, a current amplifier or AC coupled voltage amplifier, and electrical connections to the IC examination. The IC must be biased in a non-contention state but no complicated vector set is required. So possible IC damage, no physical damage occurs with all three thermal beam-induced techniques, but newer, more powerful SOMs have the potential of depositing enough power density to damage ICs because, as said in the previous slide, increasing the power density of the laser can increase the quality of the signal, but then again, there is potential for physical damage with higher power density. So next slide. So another type of fault localization technique is external localization based techniques. So the first one is externally induced voltage alteration, or XCVA. So in here, an AC choke circuit is used with a constant voltage supply. XCVA signal measures change in the choke circuit when momentary power demand fluctuations. Using XCVA can mitigate problems of large power changes with constant current biasing that can, excuse me, drop the supplied voltage below the operational values. So as you can see here in the diagram, the test device, the optical beam is pointed at the test device while there's an AC amp in the current choke as stated here. This can be how can you say this? If your current location experiences a lot of power surges, this is how they test it. So how certain chips can survive power surges or power blackouts. So even if there are sudden changes in currents and voltages, they can be sure that that externally induced voltage alterations does not render the chip fail. So the next one is, so next slide please. So SDL, or soft defect localization. Soft defects are a failure source that can be extremely difficult to localize. In general, a soft defect will produce a failing signature under certain operating conditions and a passing signature by changing the conditions. For example, these are the temperatures, voltages, and operating frequencies are common variables. So soft defects are defects that isn't as easily seen as many defects as the early ones that were discussed, because soft defects can only happen with certain parameters reached. For example, if the condition of the testing site, if the ambient temperature is like 22 degrees Celsius ambient, if and whenever the ambient temperature reaches 26 degrees, the certain chip or the certain device fails. So this is called a soft defect, because while the chip is considered faulty, but it can only be considered faulty when it reaches a certain temperature. So this SDL is a SOM technique that localizes soft defects. This is true by resistive bias, leaky gates, oxides, oxide defects, process variations, timing marginality, and etc. So SDL can also be used for both the front and the back side of an IC. So it also uses a scanned 1.3 micrometer laser to locally heat the sample IC in a fashion similar to SEI, TIVA, or Oberge. SDL requires dynamic stimulus. So this consists of cooling of the sample may be required if self-heating is an issue. So as I said before, if the device is showing soft defects, for like example, um, heating substantially, the cooling the device so that it can be tested is required. So possible IC damage. So the damage considerations are similar to those of the Oberge, TIVA, and SEI. So as we discussed before, there are no physical damages, but increasing the power will sometimes occur damage. So the last one is SIL, or solid immersion lenses. SILs essentially increase the light collection efficiency of the optical system, increasing the numerical aperture, or the NA, which is inversely proportional to the spatial resolution. So just for insight, I don't know if any one of you is into photography, but when you say aperture, is it's how big the lens opening is. So there's the lens and there's the sensor. So the bigger the lens, of course, more light can come through, that which can be processed by the sensor. So so when there's more light, also it's also needed to be considered that the resolution will lower because of too much information in the sensor. So that's just for insight. So one example of an SIL that is the most popular SIL approach is the nail, or the uh, natural aperture increasing lens, immersion lens. So as you can see in this figure, this is an example of an SDL using an SIL showing better than 200 nanometer spatial resolution using a 1340 nanometer laser source. The gain contrast indicates a passing condition. So this image, okay. So as you can see here, that it's very the image is very detailed, but the resolution is very low because of, as said before, increasing the natural aperture will lower the resolution. So the curvature of the nail lens is usually silicon or gallium arsenic, increases the natural aperture of the optical system. So the nail or sample interface must be very flat and clean, and sample thickness tailored to the nail specifications, usually 10 meters up to about 120 meters. So for the summary, um, we should know that the electron beam techniques primarily uses a secondary electron microscopy to perform failure analysis on an IC, such as electron beam induced current, or EVIC, resistive contrast imaging, RCI, charge induced voltage alteration imaging, SIVA, and SIVA using low primary beam energies, or as Ms. DELATORE said before, LESIVA. The SOM analysis methods and analysis tool developments for IC analysis are those in in the optical beam based techniques. So and optical beam induced currents, or OBIC, is a semiconductor analysis technique that employs a scanning laser beam to induce a current flow within a semiconductor sample, which may be collected and analyzed to generate images that represent the sample's properties. So light-induced voltage alteration, or LIVA, as we discussed before, is a scanning optical microscopy imaging mode that localizes junctions. Sorry. Okay. So,
So that's all for our report,
uh,
and this summary answers all what those in the learning outcomes. Thank you.
okay. Thank you. Mm, So this is for the summary. Thank you.